There is a place in the far north where the ground is never still, where the earth breathes steam, the rivers run warm, and somewhere far beneath your feet, rock is not solid. It is alive, glowing, and slowly moving. This is Iceland, and here engineers are about to attempt something that sounds less like construction and more like a dare against the planet itself, to drill a hole straight down into the molten heart of a volcano and use the fury trapped inside it to light up an entire city. For over 100 years, humans have pulled heat from the edges of volcanoes, but no one has ever dared to reach the source, the magma chamber itself, a buried ocean of liquid rock, burning at nearly 1,000 degrees, hiding in the dark a few kilometers below the surface. Touch it with the wrong machine, and the drill simply melts. Misjudge the pressure, and the well could blow out in seconds. And yet, the reward is almost impossible to believe. A single well drilled into magma could release up to 10 times the energy of a normal geothermal well. One hole, enough clean power for tens of thousands of homes, forever. This is the story of how engineers plan to drill into a living volcano, step by step, and turn the most dangerous force on Earth into endless electricity. It is not science fiction. It is built on real volcanic engineering, pushed to its absolute limit. But before any drill could be lowered, one terrifying question had to be answered. Where exactly is the magma? You cannot see it. You cannot dig down to check. A few hundred meters too shallow and you hit only hot rock. A few hundred meters too deep and the drill is destroyed for nothing. So the first stage of this project has nothing to do with machines. It is a hunt. Survey teams spread across the volcanic field with seismometers, gravity sensors, and ground mapping equipment. They listen to the earth, recording every tremor, every faint vibration that travels up from below. Each shock wave bends differently as it passes through solid rock, hot rock, and molten rock. By measuring how those waves slow down and curve, engineers slowly draw an invisible map of what lies beneath. Deep underground, the data reveals it, a vast chamber where the rock turns soft, then liquid, then white-hot. The magma is real, its depth is marked, and for the first time, a target appears on the map, a target no drill has ever survived. Now the surface transforms. On a barren, steaming volcanic plain, a construction site rises where almost nothing should be able to stand. Heavy machinery is trucked across rough ground. A reinforced concrete drilling pad is poured, thick, level, and strong enough to anchor the enormous forces that are coming. Around it, engineers build water lines, high-pressure pumps, cooling systems, power generators, control cabins, and rows of steel pipe, stacked and waiting. Then, the drilling rig itself is raised, a towering steel derrick, dozens of meters tall, bolted down against the wind and the constant trembling of the ground. This is not an ordinary rig. Everything about it is overbuilt. The pumps are stronger, the valves are heavier, and at the very top of the well sits a blowout preventer, a massive set of hydraulic jaws designed to slam the well shut in an instant if pressure from below ever turns deadly. Every system here exists for one reason, because what they are about to drill toward can kill the entire project in a single moment. And then, the drilling starts. The bit bites into the volcanic crust and begins its journey downward, 1 meter at a time. At first, the rock is familiar. Hard basalt, layer after layer, ground away by a spinning drill head as thick, dense drilling fluid is pumped down the pipe to cool the bit and carry the broken rock back to the surface. But this descent is unlike any other on Earth. With every 100 meters, the temperature climbs. 500 meters down, the fluid returns warm. 1,000 meters, it returns hot. The deeper the drill goes, the harder the Earth fights back. To keep the hole from collapsing, the well is built like a telescope. Wide steel casing pipes are lowered and cemented into the upper section. Then a narrower pipe is run inside, deeper, then narrower still. Layer inside layer, the The well is sealed and reinforced as it pushes toward the danger zone. Sensors ride down with the drill, reporting temperature, pressure, and vibration every second. On the surface, in the control cabin, no one relaxes, because they all know what is waiting at the bottom. This is the part of the project where everything can fall apart. As the drill closes in on the magma chamber, the temperature no longer climbs gently. It spikes. The returning fluid comes back near boiling. Volcanic gases begin to seep up the well, and the readings on every screen start to swing. A normal steel drill bit would now begin to soften, deform, and fail.
So this is where ordinary engineering ends, and extreme engineering takes over. The team switches to specially designed drill heads built to survive heat that would melt standard tools. Cooling fluid is pumped harder and faster to fight the rising temperature. Every meter is now drilled slowly, deliberately, with the blowout preventer armed and ready. And then, without warning, it happens. The drill suddenly drops, the torque collapses. The resistance that fought them for kilometers simply vanishes. For a heartbeat, the control room goes silent. They have not hit rock. They have hit something that flows. The drill has reached the magma. What happens in the next few minutes has almost never been done in human history. Magma surges up into the bottom of the well and instantly freezes against the cooler walls, forming a thin shell of fresh, glassy rock. This glass plug becomes the wall of a brand new kind of well, a borehole that ends, quite literally, inside a volcano. Now the danger changes shape. Through that glowing rock, heat pours upward with terrifying intensity. The fluid trapped at the bottom of the well is no longer just hot water, and it is no longer ordinary steam. Under the crushing pressure and blistering temperature this deep, it becomes something stranger, a supercritical fluid, a state of matter that is neither fully liquid nor fully gas, carrying far more energy than steam ever could. This is the prize the whole project was built to capture, but right now it is also a loaded weapon. If released carelessly, it would tear the wellhead apart. So the team must do the hardest thing of all. They must tame it. Slowly, carefully, the well is brought under control. The blowout preventer holds the pressure. Heavy steel valves are installed at the surface, one by one, each rated for heat and force far beyond a normal power plant. The flow from below is opened only a crack at first, tested, measured, then closed again. Engineers watch for corrosion because the gases rising from magma are acidic enough to eat through ordinary metal. Special heat and acid-resistant alloys line the wellhead. Cooling and cleaning systems are added to strip the most damaging chemicals out of the flow. Then comes the first real test. The valve is opened, and the well roars. A jet of superheated, supercritical steam blasts upward through the pipework with the energy of a furnace that never goes out. Pressure gauges climb and hold steady. The well does not fail. The shell of glass deep below holds the magma back, and in that moment, the engineers realize they have done it. They have built a stable doorway between the surface and a volcano's molten heart. But raw volcanic energy is useless until it is converted. So, beside the well, the power plant takes shape. The supercritical steam is channeled through thick, insulated pipes into a separator, where pressure and temperature are carefully reduced into clean, dry, high-energy steam. That steam is then driven into a turbine, a massive spinning machine engineered to handle far more heat and pressure than a standard geothermal plant could ever survive. The steam hits the turbine blades and forces them to spin thousands of times a minute. That spinning shaft turns a generator, and the generator does the final magic, and it transforms the fury of a volcano into a steady, silent current of electricity. The used steam is cooled, condensed, and pumped back deep into the ground, where the earth will heat it all over again. Nothing is wasted. The volcano becomes an engine that never stops, refueled endlessly by the planet itself. Transformers step the power up. Transmission lines stretch out across the volcanic landscape, and the energy begins to flow away from the steaming plain toward the people who will never see the danger that powers their lives. Kilometers away, a city waits in the long northern dark. Streetlights glow, homes warm, factories hum, hospitals stay lit through the night. And almost no one inside that city knows that the power running through their walls did not come from coal or oil or gas. It came from molten rock, pulled out of a volcano through a single, impossible hole in the ground. This is the quiet revolution hidden beneath Iceland. A nation sitting on one of the most violent geological zones on Earth, learning not to fear the fire below, but to reach into it, harness it, and turn it into one of the cleanest, most powerful energy sources humanity has ever touched. From the first faint tremor recorded by a sensor, to the first jet of supercritical steam, to the first light switched on in a distant home, this project tells one story above all others: that the most dangerous forces on our planet may also be its greatest gifts if we are brave enough and careful enough to use them.
A power plant standing on the shoulder of a volcano, a wall that ends inside molten rock, a city powered by the heart of the earth. Once this was a fantasy. Now it is the blueprint for the future of clean energy. If this journey into the impossible kept you watching, subscribe and follow the channel, because next we go even deeper into the engineering projects the world said could never be built. Tell us in the comments, would you live in a city powered by an active volcano? See you in the next one.
Slow it down coming out. Watch the stand, bring it over to the V-door. Give it more torque. Okay, that's tight. Clear.
We have a surge. Increase pump speed now. Maintaining pressure at 800. Keep it stable. Watch the vibration.
Emergency shutdown. Watch the bucking string. Stabilize the torque. Emergency shutdown. Watch the bucking string. Stabilize the torque.
We have a surge. Increase pump speed now. Maintaining pressure at 800. Keep it stable. Watch the vibration.
Watch out! What was that? What was that? What was that? The string just dropped.
Magma breach. Secure the rig now.
I'm on it! Hold steady!
Okay, send it down. Going in the hole.
The temperature is still rising. We need to move quickly.
Almost done with this section. Okay, hold it right there. Slow descent, watch the stabilizers.
Copy that, dropping to 2 meters.
Perfect, secure the hot zone clamps now.
It seems stable at this flow rate. Keep monitoring the structural integrity of the troughs.
The pressure on line 3 is still fluctuating. Yep. I'm adjusting the flow rate now. Looks stable from here. Okay, bring it down slowly. Watch your hands there. Watch your hands there. Looks aligned. All right, hold it steady. Move it slightly to the left. Perfect, bring it down.